Good morning, everyone, or good afternoon, good evening, wherever you are in the world. I'm absolutely delighted today to give this little lecture for the University of Aberdeen on the North Sea and net zero. So I'm Rachel Brackenridge. I'm a lecturer in geology and I'm also the programme director for the MSc in Integrated Petroleum Geoscience. So really I'm going to be talking about the North Sea and net zero, so the energy transition, and really from a geoscience point of view, as I'm a geologist. So very relevant, of course, the energy transition for engineers and for social scientists, but we're going to focus today on some of the geoscience aspects. So firstly, how do we define net zero? Well, really, where did it come from, the concept, the need for an energy transition? I think it's widely known now that the Earth is warming, and the stripes in the background of this graph show from 1850 through to present day, the global mean temperature for the world, and really this marked warming towards in the last couple of decades, really, and that's been linked to increasing greenhouse gas emissions from anthropogenic sources. And this graph is showing the CO2 emissions that are really increasing at a startling rate. So really to limit this global warming, we really need to halt our greenhouse gas emissions, and that's halt, not just reduce. These need to be stopped from entering our atmosphere. And that's where this concept of net zero came about. So it all started back really in 2015 with the Paris Agreement. That was a legally binding international treaty that aimed to limit our global warming to well below 2 degrees Celsius, preferably even below 1.5 degrees Celsius compared to pre-industrial levels. Because above 2 degrees Celsius, things are going to get really, really challenging for us to survive on the Earth. So as part of this Paris Agreement, the countries that signed up for this treaty by 2020, they needed to put forward what they were going to do to limit this global warming. And in 2019, the UK was the first major economy to commit to net zero emissions by 2050. Scotland a little bit earlier in 2045. And now a number of countries have come forward with legally binding commitments to achieving net zero emissions. So it was really in 2019 that this concept of net zero sort of entered the general public's vocabulary. And what it means is, first and foremost, a reduction in emissions. That's an important component of it. But any remaining emissions that we're just unable to eliminate from our daily lives, any of those remaining emissions of greenhouse gases are offset by an equivalent amount of greenhouse gases from the atmosphere. So you might have seen it if you've booked a flight very often, obviously not in the last couple of years probably, but if you're booking a flight, often there's an option to offset your carbon footprint by companies that go out and plant trees. So that's one way of offsetting your emissions, is to plant trees. But another way is carbon capture and storage, for example. And I'll talk a little bit about that particular technology later in this talk. So I mentioned that there are emissions that we're probably going to struggle to eliminate from our lifestyles, and let's have a look at why that is. So the role of oil and gas, fossil fuels, we're really reliant on them for our everyday lives. So today, well, this pie chart at the top right, that shows last month's national grid usage. So that's the UK's electricity usage over the month of April. And you can see that around about half of our electricity was generated using fossil fuels, and the majority of that was natural gas. So we use between 40 and 50% of our electricity that's sourced from natural gas in the UK. The remainder comes from other sources, so for example, hydroelectric, nuclear, and then there's about a third comes from renewable energy sources, so predominantly wind and solar energy. But electricity is just one component of what we're using oil and gas for in our daily lives. We really do rely on them for a whole suite of other reasons, and that's what this graph in the bottom left is showing. So we use hydrocarbons, oil and gas products, for not just energy but non-energy uses, mainly manufacturing of petrochemicals. The petrochemical industry feeds into plastics, into building our tarmac for the roads, fertilizers, a whole suite of products that come out of oil and gas. We also use a really significant amount of oil for transportation, air travel, heavy goods, and for car travel. And that's set to continue even in a net zero world. So this graph shows in grey our UK oil and gas demand, the amount of oil and gas we're expected to need to maintain the lives that we're living. So in grey you can see even up to 2050, the UK is still going to be needing oil and gas, and indeed the world is still going to be using oil and gas products. What's interesting here is that in purple, that shows the forecast UKCS production. So that's the amount of oil and gas we're producing from UK waters. And you can see that although that's in decline, even all the way through to 2050, there's a difference between, there's a much lower amount of oil and gas being produced in the UK than the amount that we're needing to use. And that gap is rather concerning, because that means that we're relying on oil and gas products to be imported from elsewhere. So there's a really important sort of social political story to be told there. So we're going to really continue to rely on, or have a need for UK domestic oil and gas exploration and production in the years going forward. So important to take away from this that even in a net zero scenario in 2050, when we are looking at net zero emissions, we're still going to be using oil and gas. Going to take a step back now and have a look a little bit about the North Sea. So I'm talking in this presentation about the UK North Sea. Of course, it extends into various other countries. But the North Sea basin overall is a really prolific hydrocarbon basin. More than 39 billion BOEs, barrels of oil equivalent, produced in the last 50 plus years of exploration and production there. So the first fields were discovered in the late 1960s, early 1970s. So we have 50 plus years of experience looking into the subsurface below the North Sea. And the image on the right-hand side, that shows all the wells that have ever been drilled in the North Sea, thousands and thousands of them. So it's a mature basin now, and that's what's being shown in this graph in the bottom left. You can see the oil and gas production per day from the 1960s, 1970s, right through to the present day. And you can see that, the production rates have fluctuated up and down along the way, but we're really in a time of overall decline. The last 5 years, we've had quite a few significant oil and gas fields come on stream. So there's been a slight increase again, but overall, this is a mature basin. And we're declining the amount of oil and gas that's being produced. So that's what the North Sea has looked like historically. How does it look today? So I mentioned it's in decline, the amount of production that's going on, but we still know that there's oil and gas out there. And this map in the top right, that shows the estimated accumulation of oil and gas that's still out there to be produced in the North Sea. Huge potential. So the size of these bubbles indicate the relative amount of oil and gas across the North Sea in these various areas. Huge potential up in the north in the Faroe Shetland basin, and out west in the Rockall Trough in purple there. It's estimated 10 to 20 billion barrels of oil equivalent remaining. So there's still stuff out there, and we know that because companies are still making discoveries. A number of significant discoveries in recent years that's actually been elevating our production. This image shows the Cygnus Alpha platform, which is a particularly significant discovery. I think came on stream in 2012, but it's a really large accumulation of gas, and it actually provides around about 5% of our domestic gas supply. So really important discovery for our energy security in the UK. If you are exploring and producing for oil and gas in the North Sea now, it's a very different world from that it was in the 1970s and 80s. There's a very good regulator, that the Oil and Gas Authority, and they're responsible for tracking and monitoring industry performance, basically every step along the process of producing hydrocarbons. So they work really heavily on monitoring and benchmarking production to make sure that companies are really maximising their efficiency, getting as much of the hydrocarbons out of the ground that they possibly can efficiently and safely, and not leaving oil and gas behind so that it's stranded and not producible down the line. They also play a really important role in tracking emissions of the industry. So there's a real mandate now to reduce emissions of operations. That includes flaring, which is very highly regulated now. So flaring is required in order to safely produce an oil field, but really minimising that is very important. So yeah, a lot of monitoring and benchmarking going on today in the industry. Looking to the future, so I mentioned we have 50 plus years of experience now in exploring for and producing oil and gas. And as a result of that, there's a huge wealth of knowledge, skills and expertise in working in the subsurface in the North Sea. And we're also in a really good position that there's a huge amount of potential for low emission, low carbon energies to be set up in the North Sea. So this map shows a number of projects that are ongoing or planned in low carbon energies. So that ranges from carbon capture and storage, hydrogen, and then offshore technologies such as offshore wind farms, wave and tidal energies. And I'm going to talk a little bit about a few of these in more detail. So we know that we've got the skills, the knowledge, the expertise to make these things work in the North Sea. We also have a huge amount of infrastructure in there that makes it very accessible for the engineers to make work. And we now, importantly, have a really good mandate from the government to make this energy transition a reality. So the North Sea Transition Sector Deal, that was released just a couple of months ago, back in March. And it really set up a set of deliverables that the government wants to make happen to ensure that people working in the oil and gas industry are able to transfer over to renewable energies in the energy transition. And we really don't lose those skills and expertise. So they set out 5 key deliverables, which are highlighted here. I've highlighted 3 of those have a really significant subsurface component. And that means that geoscientists are really going to have an important role to play in delivering these 3 technologies. That's firstly supporting the delivery of CCUS, carbon capture, utilization and storage. Secondly, the diversification of oil and gas in the supply chain into new energies. And thirdly, in supporting the development of hydrogen production. So I'm going to talk through each of these three aspects from a geoscience point of view. Starting with carbon capture and storage, so abbreviated to CCS, or sometimes CCUS for carbon capture, utilization and storage. So it's widely sort of accepted that carbon capture and storage is really critical for us to achieve net zero. So what is it? So it's the process of capturing carbon dioxide from large point sources. So that could be an industrial centre such as a cement works or a power plant. So we capture that carbon dioxide and then transport it and deposit it somewhere so that it's not going to enter the atmosphere. And that tends to be in the subsurface. So that carbon dioxide, it needs to be safely and permanently stored in the subsurface. And when I say permanently, I'm talking geological timescales, thousands to millions of years that it's going to be safely contained there. So carbon capture and storage, it's a huge engineering challenge to make work. It's a huge social, political and economic challenge to make work commercially. But I'm going to talk primarily here about the subsurface challenge, the geological challenge to make this work. So if we focus in on this offshore aspect of it. So the geologist is really important in determining a suitable site for carbon dioxide storage. So I'm summarising that in site risking. We're responsible for telling the engineer where they need to drill their well and inject the CO2. So what do we need to understand where might be suitable for this? Well, these four aspects are really essential. So we need reservoir identification first and foremost. So I'm naming reservoir as any rock that we're able to inject CO2 into. So in order to inject CO2 in, we need a porous rock. So that rock needs to have pore spaces in between the grains that can be used to store the gas. So that could typically be a sandstone or a limestone, for example. Really, we've been looking and mapping these reservoirs in the subsurface for many years. They're very similar to, or sometimes they are, old oil and gas fields, but we can also look for saline aquifers as well. Secondly, CO2 injectability. So the engineers don't want to inject CO2 in the form that it is in the atmosphere as a gas. They're really looking for that carbon dioxide to be in the correct phase. They want it to be in its dense form, in a liquid form. And for that to happen, we need the right pressure and temperature regime in the subsurface, and that tends to be below about 800 meters below the seabed. So we're looking for reservoir rocks that are at the correct depth in the subsurface. Thirdly, once we have a reservoir, we know its extent, we want then to be sure that the carbon dioxide is going to remain in that reservoir over a geological timescale. So for that, we need to understand the rocks above the reservoir and make sure that they're not going to allow any leakage of CO2 up towards the seabed. And I've called that seal integrity. We want to make sure that the gas is going to be sealed within that reservoir. And finally, reservoir capacity. So this feeds into the economics of the project, the feasibility of the project. We need to know, the engineers need to know how much CO2 can we inject into this storage site, so we can put some figures on it. So we know in the UKCS and in the North Sea, we know that there's a number of potential storage sites that have had a first identification, and these are targeting saline aquifers, so large saline aquifers in the subsurface, and also depleted or old oil and gas fields across the North Sea, both in the northern North Sea and in the southern North Sea. So huge potential here. So that needs to be done before a CCS site has been identified. As we're injecting, it's really important to understand the reservoir characterization in a little bit more detail. So the geologist is looking to understand the nature of the pore spaces between the grains in the rock, to understand how the fluid is going to flow through that reservoir as it's injected. And there's also an important component of understanding the mineralogy, the types of minerals within that reservoir, in order to understand how the CO2 is going to react with the reservoir. After CO2 injection, we also need geoscientists to monitor the site, so geophysicists particularly. I've taken this example from an existing CO2 storage site. The image on the left, that shows a seismic image of the subsurface, an image of the subsurface before any CO2 was injected into the reservoir. On the right, there's evidence of gone back and done another survey after CO2 injection and have compared the two data sets to see what the difference in those data sets is. So this is a difference map. And what you can see is these booming reflections in the center of that seismic image. That's the CO2 that's been injected into the reservoir. Really bright amplification of the reservoir with the CO2 in it. But most importantly, above that reservoir, there's very little difference between the seismic data collected before the CO2 injection and after the CO2 injection. And that tells me that the seal that's over the top of this reservoir is really doing a very good job of holding that CO2 back. No CO2 is really escaping up towards the seabed. So geoscientists need to go back regularly, every sort of 5 to 10 years and reassess these storage sites to make sure that that CO2 is staying where it's meant to be and not escaping. So it's an important aspect to the geoscience after CO2 storage has taken place. I want to highlight that all of these processes that I've highlighted relating to carbon capture and storage are all currently being used by petroleum geologists. So really similar skill set, just reapplying them to a new problem. The second energy I want to talk today about is hydrogen. So there's a lot of excitement about hydrogen energy as a way to really transform the UK energy system in a net zero world. So hydrogen has been plugged as a replacement for natural gas and can be used for transportation and potentially can be used for heating our homes and using in cooking and household uses. So it's a really important and exciting new energy. There's a number of different types of hydrogen. I'm going to talk today about green hydrogen and blue hydrogen. So green hydrogen, that's hydrogen that's been produced directly from renewable energy sources, so from wind or tidal or wave energy, and it's produced through a process called electrolysis. Blue hydrogen is generated directly from methane, from natural gas, and that's been done through reforming, and it's typically used alongside carbon capture and storage. So let's look first at blue hydrogen, because that's closely related really to the oil and gas industry. And there's a number of projects ongoing or getting going in the UK, around the UK, testing this the use of hydrogen. I'm going to use this example from the Acorn project, which is just around the corner from Aberdeen up in the northeast of Scotland. So the theory here is that we take natural gas that's being produced from the North Sea, and it's made into hydrogen at the St. Fergus production facilities. That hydrogen can then go off to market for uses in eventually in domestic heating once the infrastructure is in place, but can also be used to generate electricity and for transportation. And the byproduct of that process is CO2, which can then be transported back offshore and injected into the subsurface for CCUS. So you can see that there's a really important subsurface component to this, both in making sure that there's a feedstock of natural gas, that we're producing natural gas from the North Sea to facilitate this process, and to make sure that the CO2 that's produced as a byproduct is safely and securely stored in the subsurface. So that's blue hydrogen. I think that's going to come first. And then we have a look at green hydrogen. Now, green hydrogen is really interesting. So it's formed directly from renewable energy, so from solar, wind, tidal energy, wave energy. Now, what I've shown here in this graph, this is the energy usage, the electricity usage in the national grid in the UK for the month of April. And you can see that there's really a sort of sawtooth pattern to it, and that's relating to the energy demand in the day versus the energy demand at night. So during the day, when we've all got our our lights and our computers on and industries up and running, there's a much higher energy demand than at night when we're industries closed down and we're all lights off and in bed sleeping. So that's each of these sort of sawtooth shapes is one day. I want to sort of direct your attention to where the energy is coming from at these various times. So firstly, in yellow, that is our solar energy. That's the electricity that's being produced from solar panels. And seems like stating the obvious, but we can only generate solar energy when the sun is shining during the daytime. So we can't generate solar energy at night. The second aspect I want to draw your attention to is the wind energy generation. That's highlighted in this light blue colour. And you can see that early in April, there's this big chunk of this blue colour. So that tells me that it was a particularly windy week in April, towards the start of April, and we were able to generate lots and lots of wind electricity from wind. But as you move through April, you can see in mid-April, really there's no wind energy being generated. That tells me that the wind wasn't blowing, it was really calm conditions. And to make up that shortfall in energy, we had to turn up the gas power generation and generate a lot of electricity from gas, which is highlighted in this sort of orange colour. So where hydrogen comes in to this scenario is, hypothetically, we knew that there was a lot of wind energy being generated at the start of April. If we were able to convert that energy into hydrogen and then store it so that we could use it in mid-April when there was no wind energy being generated. So hydrogen from renewables alongside storage is really essential and facilitates balancing generation capacity with demand. So it's effectively like a massive battery. We're able to store that energy for a later date when we need it. And to store that hydrogen, the subsurface is a really good large place to store it. So there's a few storage options. We can store hydrogen in porous rocks, very similar to those I described for the carbon capture and storage. And there's also research going on into storing hydrogen within salt caverns in the subsurface. But for both of these options, the geologist is required in order to understand the distribution of those reservoirs, their thicknesses, their depths, to understand the capacity of these reservoirs for storing hydrogen safely and securely. So that's hydrogen. I want to spend just the last few moments of this little lecture looking at how geoscientists can support the offshore renewable industry more generally. So over the last sort of couple of decades, our horizon line has really changed in the UK with the installation of wind farms. We now get a really significant portion of our electricity generation from offshore wind. But there's other offshore renewable energies that are really being tested in earnest now, so tidal energy and wave energy. And all of these offshore technologies, they require installation on the seabed. They require foundations or mooring points, and a geologist can really contribute to understanding that substrate. And that's demonstrated in this example that I've taken from the southern North Sea. So on the left-hand side, this is a map of a proposed wind turbine farm. The wind turbines are indicated in those red dots. So you can see that it's a very strict grid pattern that's been proposed for this wind farm. But underneath those red dots, you can see the contours of the seabed. It shows that, yeah, it's quite an organic shaped seabed. There's lots of highs and lows. And also in yellow is highlighted this Botany Cut Formation. This is a specific type of substrate, type of rock on the seabed that's different from the rest of the seabed. And understanding the distribution of this different type of rock means that it will have different consolidation properties, permeability properties, different strength. And as a result, when we're installing moorings or foundations onto the seabed, different rocks will have different properties, and therefore you might need to tailor those engineering designs to the properties of the seabed. So really important to understand what the properties of the rocks at the seabed are for these facilities to be installed safely and cost effectively. So to conclude, I hope I've shown or demonstrated over this very short little lecture that geoscientists really will play an important role in the energy transition, but also that the oil and gas industry, its employees and skills really are going to play an important role in meeting net zero. I think if you take one thing away from this lecture, it would be that really the oil and gas industry is complementary to the energy transition. We're wanting to work with the energy transition, not against it. And there's a lot of transferable skills that are shared between the two industries. I've spoken primarily about offshore energies and energy systems, but geologists are also going to play a really important role in other aspects of the energy transition in the onshore. So geothermal, for example, nuclear waste disposal, and providing minerals in a safe and sustainable and responsible way in order to manufacture these technologies and provide minerals for batteries, particularly as we go into electrification of transportation. So final slide, I just want to introduce our MSc programs. We have a Centre for Energy Transition that's being set up. I think the grand opening is this month. So I've put the website link there. Do have a look at the energy website and what we can provide. Here in the Department of Geology and Geophysics, we've got a number of really great MSc programs that aim to provide the skills that are required to enter these energy industries. So I'm happy now to take questions about these MSc programs or anything that you've sort of seen in the lecture today. Happy to open up for questions, but thank you for coming along and having a listen. Let me just open up my Q&A. Yes, any questions about the role of geoscience, or any questions about the master's programs across the energy programs? I'm happy to answer. Okay, so out of the types of energy I've mentioned, which one do I think will be the most popular in the future? That's a fantastic question. I think in order to make net zero a reality and successful, I think really integration of multiple energy sources are going to be really important. They've all got a part to play in making net zero successful, and I think probably we'll see an evolution of the dominance of these different energies as we go go through the energy transition. So I think immediately blue hydrogen probably is going to be a really good way to make moves towards net zero. But then over time, as we develop more and more low carbon energies, green hydrogen might overtake that down the line. So a little bit of an evolving mix of energies, but really I don't think there's one energy that's going to tick all the boxes for us. It's really going to be a case of integrating multiple energy sources so that we're versatile in where we can gain our energy from and adaptable. But yeah, great question. Next question, do you think it'll be possible for Scotland to become a net zero society by 2045? That's a very intriguing question. So, I mean, it has to be because it's been stated that we're going to be, and it's a legally binding statement, commitment that we've made. But yeah, we're making very good progress in this. But yeah, it's gonna be a challenge, and it's gonna take quite a bit of adapting to get there. But yeah, there's a huge amount of investment going into making this transition happen. And I do think there's a lot of commitment from companies, from organizations, but also from members of the public in making this happen. So yeah, if we all work together, I think we'll get there. But yeah, it's going to be hard work. We're going to need some pretty good people working on this problem to get there. I see Anna's put in the link to our Centre for Energy Transition website, so do have a look at that. Another question, is this lecture given today similar to what's taught on the geology programmes? So I've sort of given you sort of a glimpse as to some of the themes that we touch on. In reality, for the PGT lectures, we really try to have a lot more interaction, a lot more sort of exercise-based tuition. We really aim to provide students with the skills that are going to really enable them to go straight from education into employment. So not only the technical knowledge of the subject, whichever master's program you sign up to, but really also the transferable skills that are required to succeed in the industry. So from integrated petroleum geoscience, for example, we have a huge component of group work, which really helps you to work in teams, and a lot of presentation skills that are also put into practice through the course. But yeah, it's giving you a nice indication of some of the themes that we do discuss over the course of the year. Great questions. Any other questions or comments? So how relevant do you think the petroleum geosciences, given the storage of CO2 and hydrogen, should become more heavily used? Does the course cover this, or is it more directed towards finding and producing hydrocarbons? So we're currently very much focused at the moment on the oil and gas exploration and production, and are now building in much more CCS based stuff, understanding subsurface storage component of that. So this is evolving as time goes on, and we're trying to get more of this into the course so that we can remain really relevant to what the industry is looking for in their geoscientists. But as I mentioned, all these skills that we use in oil and gas are highly transferable into these other technologies. So good question. How effective are other countries willing to embark on net zero emissions, taking into account developing countries and the exploration of oil and gas is steadily rising in developing countries? Absolutely great question. Yeah, so I've discussed a little bit about the geoscience aspect. There's a huge implications to the energy transition from the social aspect, and this is covered really well in some of the master's courses that are provided in the Centre of Energy Transition at the university. One thing that, yeah, the UK is really well placed for really getting the ball rolling, or the North Sea in general. Norway's doing a fantastic job of also developing these technologies. Uniquely, the North Sea, because we're such a mature basin, we have the infrastructure. We've done the trial and error of making, oil and gas work. There's a lot of skills there that are transferable. That means that we're in quite a unique position to really get these technologies up and running at a commercial scale, to test them out, proof of concept, and then share those learnings with other countries in order to make the energy industry more sustainable, I guess, on a global scale. It is a global problem, and it needs to be sort of globally tackled down the line as well. But yeah, it's going to be a challenging process. Hope that answered that question. Will gas become more popular than oil in the near future in terms of production to reduce CO2 emissions? Yeah, that's a great question. I believe so. So we've already many countries are making really good progress at reducing their dependency on coal for this reason. So coal-powered generation is now very much declining across many countries, and that's for that reason, in that burning coal does produce much more emissions than oil and gas, and then gas is much cleaner than oil. So the vast majority of our fossil fuel burning for electricity in the UK does come now from natural gas for that reason. So I think we will see a reduction in using oil for energy generation. The challenge is going to be removing oil from other industries, such as petrochemicals. It's a really important feedstock for the petrochemical industry, and I'm always amazed at how much of our daily lives the materials that we use are generated from petrochemicals. And there's also there's always going to be a challenge in a global shift in our transportation away from oil and gas as well. But yes, gas absolutely is becoming more and more popular for electricity generation. Great question. Would you recommend studying petroleum geology or something more focused on renewables? I don't have a fantastic answer to that, I'm afraid. What I'm seeing is, as much as there's a huge amount of discussion about the energy transition and a lot of buzz and coverage in the media about this, what I'm seeing is that, particularly from the geoscience point of view, a lot of these technologies they've not been commercially upscaled to work at a commercial scale, and as a result, there's not that many jobs really in it at the moment. I think what's going to happen is petroleum companies are going to adapt. So yeah, I think if it was me, we're in this sort of in limbo time where we're not really getting the massive feedstock of jobs in renewables. So perhaps going into petroleum first, focusing on becoming a really good petroleum geoscientist, and then trying to expand your skills into renewables would maybe be a route that I would choose. But yeah, it's a really challenging question to answer. Question from Anna. Yes, do you imagine that geopolitics will become an ever more important topic to teach, particularly as oil and gas rich nations become slightly less powerful players in providing energy globally? Yes, absolutely. There's a huge amount of, so I've talked mainly about the North Sea oil and gas here, but huge potential in many emerging basins, still a lot of frontier basins there that are really just getting started. And it's going to be a huge social political challenge to make sure that that transition is just across all these different countries. Lots of questions coming in now. So do you see geoscience job opportunities picking up again as we come out of the downturn and as operators move into CCS hydrogen? Yes, absolutely. I think it's clear that we're going to be really reliant on, or there's going to be a demand for oil and gas for many, many years to come, talking about decades to come. So we still really need good geoscientists to enter that industry and keep that industry vibrant and productive. And yeah, a lot of the companies now are releasing very important statements on their intent of how they're going to deal with the energy transition. A lot of companies are committing to developing CCS and hydrogen. So I think this is going to be an ever expanding area of opportunity. And I like that you say job opportunities. I do think it's a really exciting area to be getting into at the moment because it's so dynamic and it's transforming at such an exciting rate that, yeah, really exciting times to get into the energy industry. A question from Ollie. Do you think mainly blue hydrogen fields are relative to conventional gas fields? We're likely to see many maturing gas fields transitioning to sites for blue hydrogen CO2 storage. That's a really nice concept. So yeah, I'm a strong advocate for blue hydrogen. I think it's a really, really neat piece of technology that really ticks a lot of boxes in making the energy transition a reality. And yeah, injecting CO2 into depleted fields or maturing gas fields is a really nice, tidy way to cycle that process. So we've been injecting CO2 into oil and gas fields for many, many years in order to enhance the production rates, enhanced oil recovery, for example. So reservoir engineers and geoscientists, yeah, we have this skill set in doing this. And yeah, it'd be a really nice way to sort of integrate, again, that's integrating these energy systems together. I think is the way forward to make it work. Petroleum geology is a science that uses the knowledge of petroleum systems to discover and extract petroleum resources. Maybe future courses should be called something like petroleum mitigation use the direction to attract the right interest. Yes, absolutely. It's a very evolving subject at the moment, and it is a science. I'm going to say geoscience is definitely a science. Yeah, ever evolving at the moment at an incredible rate. Question from Kirsty: how does your work contribute to the energy transition? So very much looking at, to pick up from a question that we had earlier about gas. I think, yeah, ensuring that we have a good feedstock of gas coming into the UK, for me, is really, first and foremost, really important, because that gas really does ensure that we have a nice energy stability and security in the UK. So we have in the past, not so many years, in the past couple of years really, there's been some close calls when energy demand is particularly high and we're relying on imports. We've come very close to running out of gas in the country. And if that happens, we're looking at, rolling blackouts and, not being able to switch on our heating on demand. And that's really concerning. So I think making sure that we have this really good supply and reliable supply of gas is really important. And then down the line, if that can feed into to generating blue hydrogen. I think that's going to be a really important aspect of my research. That's where my drive comes from. Good question. Non-technical question. Would like to know if this lecture will be made available. Yeah, absolutely. I believe this is going to be put on to the University of Aberdeen YouTube website, alongside a whole suite of other little lectures that have been done and are continuing to be done by the university. So there's a range of different subjects actually already on there, including some of the aspects that have been sort of asked about in the questions here on the social side of the energy transition. And there's also some a lecture on the economic side of hydrogen as well, which is really really interesting. So do check those existing little lectures out, and then this one should be going up there at some point as well. Excellent. Well, with that, if there's no other questions, I think we'll wrap up. Thank you very much for coming along today and for engaging with some really fantastic questions. Really look forward to sort of seeing some of you hopefully in one of our master's courses, but regardless, seeing this next generation of fantastic geologists going into the industry and really making this net zero a reality. We're going to need some really bright minds to step up to this challenge, and I'm really excited to see how we get on doing it. So with that, I will close the session. Thank you very much for coming along.